PDB tools. There it is. Was it this one? No. Phoenix reduce. Exactly. Minus 3. Okay. Phoenix reduce. Trim. So there we are. That's it. Okay, so I run this command. Okay. Phoenix reduce all dark refine underscore 28.pdb minus trim, and move that into a new file called all dark underscore refine underscore 28 underscore no age.
Just cut out of
Remove the hydrogens. So let's take a look at how that file looks. Yeah, and see, it keeps all the header information and all the data. Okay, and so now we can take a look at how this behaves. So we can look at the file here, okay? And just make sure that it's nice and clean, and I can see, yeah, so this looks nice. Okay, everything looks nice and clean. Okay, good. So now we can take this and we can go into CCP4. Okay. Do you have a project for this guy in CCP4? Yeah, this one, isn't it?
Oh yeah.
Yeah. So now later we go here to SFO.
So
Yeah, the
what's this for?
So SFO will take, see, you generate structure factors and faces from coordinates.
From with
Exactly. And then append FC and FIC. FC and FIC means calculated structure factors. Remember, FC means FO is observed, FC is calculated, and FC is calculated phase.
Okay, cool.
Okay? To FP and SIGFP. FP is observed. I don't know why this in CCP4 they don't use FO, they use FP. Okay? So and SIGFP are the experimental ones from existing empty set file, and scale input FP to FCalc. Remember, this is what I mentioned, that because you're calculating them, and you know how many electrons is around every single thing, you can calculate the absolute scale of the calculated data, of the calculated structure factors perfectly. So that means that now you can use that to scale your observed structure factors so that they are the perfect absolute scale. You see? So what do we use for this? Well, we use our initial data. Okay, so where's the initial data? Is it all dark, or what is it? So what's the dark empty set file?
The dark empty
So we need to go here like this. Yeah, we're here. Okay, where's the dark empty set file? All dark, and then this is the PDB file. Wait, yeah, this is the PDB file. Okay, so we go all dark and we go refine 28 and we go for this one, the no age one, isn't it? Yeah. So wait, let me write it here. Generate model F. So generate all dark FCs. Okay, for scaling and extrapolation. Okay. So, and now the empty set in is of course the raw empty set file.
Yeah, I think
so they should be here, isn't it? All dark RefMac 1. Nope. Crackery. Where is it? It should be in all dark. All dark truncate.
Yeah.
Okay. Okay. And we call it all dark underscore SFO1. Okay, that sounds good. Okay. And now the resolution, we're gonna cut it out at, for example, 35 angstroms to what?
1.47.
1.47. Okay. Okay. And we just run it. Okay. Let's do one thing. FCalc. Okay, that's fine. Well, no, let's call it FC dark, okay, and PC dark. in this way. So the labels
Oh.
of this, we call it already dark and dark because later you may combine it with the different time points. And in this way, it's clear what it is. Okay, so we just run it and we just tell it to overwrite it. Okay, so now it's done. Okay, so now here we have the new data files. Okay, and so if you want to, we can take a look at it. All dark, refine 28, no H. And now, yes, and now we can open empty set. Then we can take from here. See, all dark, sorry, here, all dark SFO, okay? And so we can take FC dark and VC dark, okay? And we run it. And so these are the calculated map. So this is the calculated map, okay? And so here we have it. And notice, for example, that this guy doesn't appear, okay? So we need a, so you see, it only appears later, okay? The reason is that it must have a very high B factor, okay? So that's okay. I mean, if that's the case, that's the case, okay? And so you see, here we have everything the way that it should be, okay? So now we have all the data that we have collected, okay? See, and this one appears, but only at very low sigma. Remember that here we simply don't have really a sigma level because we have no noise whatsoever. Isn't it? Because it's calculated. Now we can open it, this one, and we can generate it like this with the experimental structure factors. And see, these are the experimental structure factors. And you see we get, see, for example, here, these guys appear at a higher sigma level. You see? 0.7.
Experimental.
Exactly. While in this one, they appear at 0.42. You see?
Oh.
So that's what I meant. That. Okay. And so here we are. Okay. So, but as you can see, it fits very well with each other. Yeah, there is no. Exactly, because you have in general a very, very good data set and you've done a good job refining. Okay. So that means that we are ready to go. Okay. So the next thing we're gonna do is, now that we have this, now we can generate our own pair of densities. And so to do so, for example, which one are we interested in?
180.
Let's go for 180. Okay. So now the first thing we need to do is run CAD. So CAD here. CAD is a program to combine different empty set files into a single empty set file. Okay? And so what we do is, you see, we're gonna write it here, combine all dark with FCs with 180 picoseconds. Okay?
Oh, okay.
And so we take the first one that we're gonna take is all dark SFO, okay? And now we are going to show selected columns, list all columns, and we want all of them here, okay? The only thing that we're gonna do, just in case, is we're gonna call this F dark and sig F dark. Yeah? Notice the difference between F dark being the experimental one, FC dark is the what's it called, the calculated one, okay? And now of course we need to add a second one. And so the second one will be the 180 picosecond one here, 180 picoseconds, this one, isn't it? Yeah, but it needs to be the truncated one. So 180 picoseconds truncated, this one, isn't it? Okay. And now we go for selected columns, we list all columns, and now we cannot have a double free. So the system will only accept one. Exactly. So that's why we're going to delete the free one here. And also we do not want to have the intensities.
Oh yeah.
Just the structure factors. And I'm going to rename the column F180 picoseconds and F180 picoseconds so that we know what they are, isn't it? Okay. So, and now we're gonna call it 180 picoseconds CAD.emptyset. CAD because the program is called CAD. Okay. So, and now we're going to provide the resolution limits, and here we're going to set it to 35. Here we're also going to set it to 35. And what is the maximum resolution of the...
180.
Yeah. Yeah. Oof, 21% rotamer outliers. Yeah, you're fucked. That is terrible.
Let me check. The original.
That's restrained?
Oof.
Huh? Yeah, 20% rotamer outliers. That is terrible. Absolutely terrible. Yeah, well, you have to deal with it. That's part of
1.52.
1.52. Okay? And so we set it to 1.52. Okay? This is just to limit.
This is the second one.
Yeah, it's file number 2. Okay? And that's it. We just run. Okay? And it's done. Okay? So now, if you open it, we can use VuHKL to look into the general set of data and see. We can see that we have 2 data sets in the one file. Okay? One data set made out of fdark, sigfdark, fcdark, and vcdark, and another one made out of f180 picoseconds and sigf 180 picoseconds. You see? We can check the summary and we can see that in general we have completeness and resolution, so very, very high. No issues whatsoever. Okay? Good. So now we take this, okay? So, and the next step is to scale it. Okay? Now we need to scale the 180 picoseconds to the fdark, which we have scaled itself against the fcdark. You see? So now we will use the fdark, which has been scaled to fcdark, to scale the 180 picoseconds so that we have everything in the same scale. Okay? So to do so, we use the program scale it. Here, scale it.
Scale it.
Okay? And so, scale refinement using scale it. Do not include anomalous difference data. Perform cross comparison. Okay? And so we just take our 180 picosecond dark and see the FP is 180 is f dark, and the first derivative is f180 picoseconds. It's going to try to scale the derivative to the dark one. Okay? Now, yeah, exactly that. Okay? So, now, the resolution scale that we're going to use is 10 and 2.5.
Why only?
Yes. So the scaling is going to happen everywhere. Okay? However, the scale factor is going to be calculated only in this range. The reason is that the data that is too far out, so too low resolution, is very, very strong. So if you include it, you can dominate the scaling of everything.
Oh, yeah.
And because it's very strong, it may actually be close to the saturation of your detector, and therefore may underrepresent what the actual value should be. You see what I mean? So if your detector has a saturation curve that looks like this, and you're somewhere here, maybe actually your value should not be this one, it should be maybe here. You see what I mean? But because you're close to saturation, it's a bit lower than it should be, because it's not in the linear range anymore. And so that means that it can do weird things with your scaling if you have something like that. It doesn't affect the refinement very much, but it can affect the scaling quite strongly. On the other side, very high resolution data can have, so first of all, is much weaker, but also because you see it much fewer times, the standard deviation may be abnormally large. So that means that two values may have two very different, so the values on the two data sets may be very different, but because the standard deviation is very large, they may not be significantly different.
Oh, yeah.
You see what I mean? So that may be that one value is 50 and the other one is 100, but it may be that your standard deviation is plus minus 25. And so 50 and 100 with a standard deviation of plus minus 25 is not significant, because both of them could be 75 and you wouldn't know. You see what I mean? So therefore, the very high resolution values can affect the scaling factor by making it too significant. You see, making differences or pointing to differences that are not really differences. The region where you have strong peaks but still far away from saturation with small standard deviations because you have measured them very a lot of times is this region 10 to 2.5. Therefore, which is sort of the medium resolution range, and so therefore for calculating the scaling factor it's better to use this region. However, the scaling factor will be applied to the entirety of the dataset, not only to this region. Okay, so then the next thing is you use scale and anisotropic B factor. Yeah, you apply Wilson scaling. Remember, Wilson scaling is from the Wilson plot. Okay, and you weigh the observation by their SDs. So that's the standard deviation. So that strong peaks with low SDs will be more important than weak peaks with large SDs. Okay, so and that's it. Okay, so this is it. Yeah, so now let me write it here. Scaling 180 picoseconds to all dark scaled to FC dark. Okay, and so now we run it, and that's it, done. Okay, so now we have the data. Now the next step, with this you could extrapolate. You can use this, talk to them. They might have a better job for might have a better script for extrapolating, but you just talk to them. They will give you the scripts and whatnot for that. Okay. However, for looking at the difference map, okay, this is a bullshit thing from Phoenix. Phoenix cannot take the same file for both maps in the difference map, or for both datasets in the difference map. You see?
To separate them?
Yes. So now we need to use SF tools to separate them. So now that we have scaled them, we separate them. Okay? So now we go to SF tools here.
Yes, tools.
Okay. And so separate all dark 480 picoseconds. Okay? We take this one and we say delete columns. Okay, and now edit list. No, sorry, edit list. Nope, delete another column. And so we want to delete. Now we're gonna do a dark. So we delete FC dark, VC dark, F180 picoseconds, and CF 180 picoseconds. You see, and so what remains is the dark data. And so we call it dark 480 picoseconds. Okay?
Oh, okay.
And so we run it. And now we delete F dark and CF dark. And this is 180 picoseconds for dark. Okay? Okay? So now you need to use these two files for generating the difference map.
These two need to.
Oh yeah, sorry. This needs to be FC dark and VC dark. Yeah. And so now what will remain is the 180 picosecond data.
And it's not for dark.
What?
For dark here.
It's 180 picoseconds for dark. Because the only reason for having this one is for comparing it to dark.
Oh, okay.
So now we have it. Okay, and so now we can go into Phoenix, okay, and go to difference maps, this one,
Yep.
okay, and now we run 180 picoseconds, minus dark, fully refined and scaled, okay, so we take 180 picoseconds dark SF tools for dark SF tools, and dark for 180 picoseconds. You see?
Oh, okay.
And you see now we have F 180 picoseconds versus F dark. Okay? The resolution is still the same, isn't it? And the last thing we need to do is take the final refinement.
Yep.
Okay?
Non-H.
Nah, doesn't matter. Okay? And so now we can run it. Okay? And no multi-scaling. Because now we have it. We have scaled it ourselves much more accurately. So, run it. So this is your last map. Okay? So this is your proper map. So we can open it. Hey. And here we have the map. And we can see quite nicely those differences here. Let's go, what's the tryptophan? Well, we can go to 373 and it's right next to it.
Yeah, here.
Yeah.
Yeah.
Okay, and if we set it to 3 sigma, here you have
Yeah.
the data. And it looks quite nice. So we can open, what was it? Refinement 8. Sorry, FOPS 8, wasn't it? 42. 42.
Oh.
Yeah, the old one.
Oh, the old
42.
one. Okay.
So we take 42. I just want to do the comparison to see how. Okay. And so we can see the difference. So we can take
Which one is?
this one, color. If it still doesn't look as nice, the one thing we can do, so you can see after the scaling.
Blue one
Yeah.
is after school.
Sorry? The green and red one is after scaling. And so is it cleaner? A bit. I don't know. Doesn't look hugely different. Okay. See this one, we can see a bit more. Yeah. So, I mean, if you want to, we can run it also with multi-scaling. See, then it looks a bit stronger here if you want to. Okay? This guy here with that multi-scaling done by it. But okay, either way, okay? There you have it. Okay, so that's the map. Okay?
Final
Yeah,
difference.
that's your map now. Okay? So, and if you want to do extrapolation, okay, the extrapolation can be done now with the map that you just, with the structural factors that you just get generated on Scale It. So this file here contains all of the data that you need to extrapolate and to start producing the extrapolated structure factors and start refining for the 180 picosecond structure. Okay? So, Yuhei, would you have a bit of time to show him how to extrapolate?
Oh, okay.
Yeah, good. So he's generated his first extrapolated map. Can you come real quick and I'll show it to you real quick? So, see, it's this one called 180 picoseconds underscore CAD underscore scale it. Okay, and so what he has is F dark and sig F dark, FC dark and phi C dark, and F 180 picoseconds, sig F 180 picoseconds. I'm talking if you need to modify the name of the scripts and whatnot. I mean, of the variables. Those are the variables, but he can show it to you later as well here. Okay.
Okay.
But yeah, so if you can give him a hand with that part, that would be awesome.
Okay.
Okay. And yeah, so that's sort of the next step is you can see it's time consuming, but hey, you can get the actual structures by the end of it. Okay. Yeah. And hopefully, Tom, by the point